Okay, so we're going to get closer to our main goal, which we'll find in 8.3. So in 8.2, we're going to pick up this idea of the transition matrix, which I introduced at 8.1, and we're actually going to do something with it. So in 8.1, we never really did anything with the transition matrix. We wrote it down for some Markov chains, but we never used it to compute anything or solve any problems. But that's about to change. We're going to start using it to solve problems, and I'm going to show you how here in 8.2. So as a motivation for what we're going to do and why this works, I want to basically revisit an old example. So we've had this weather example that I've been using over and over again. It's this Markov chain with two possible states. Either it's sunny today or it's rainy today. That's all we're allowing. And if you remember, the transition matrix looked like this. I think I have the same numbers that I did before, but maybe not. Anyway, right, sunny, rainy. This should be 3/4, 1/4, 1/3, 2/3, I believe. Maybe the numbers aren't quite the same as they were before, but we'll just run with this. So let's suppose this is our transition matrix for this weather example. So the probability of it being sunny today and then transitioning to sunny tomorrow is 3/4. The probability of it being sunny today and it's rainy tomorrow is 1/4, and so forth. That's what these numbers represent. So these numbers represent probabilities of going from one state to another over the course of one day, or one step, if you will. It's one step of the process. Just the transitions over one step. But we've already seen that we can answer questions of the type of the following. What is the probability that if it's, say, sunny today, and then it's rainy, not just tomorrow, how about 2 days from now? 2 days. So this is like asking about a probability, not after, about transitions, not just after one step, but after 2 steps. So that's the kind of question we want to be able to answer. We've already actually answered this question in this example. Let me remind you how we did that. What did we do? One way we approached this was, let's draw the tree diagram. And I'm going to do that again here because it's going to help be helpful in illustrating something that we'll want to take note of. So let's draw in our tree diagram. And I need to go out 2 steps, 2 days from now. It should be rainy. So maybe our tree diagram looks like this. And I need to label the edges. And the edges should have what? This should be 3/4, 1/4, 3/4, 1/4, 1/3, 2/3. All right, so we just labeled the different probabilities. And now if I want to answer this question about the probability of it being rainy 2 days from now, I need to find any path that ends on rain after 2 steps, that ends on rainy. And I need to multiply the numbers and add them together. So there are 2 such paths, right? There's one that starts at rainy here and it goes up to sunny and then it goes to rainy. That's sunny, sunny, rainy, or there's sunny, rainy, rainy. Those are the only 2 possibilities. And so I need to multiply both of those and add them up. So I need to take 3/4 times 1/4. Yeah, let's do that. 3/4 times 1/4, and then I need to add 1/4 times 2/3. And that's some number. I'm not really interested in what the number is at the moment. In fact, I want to leave it in this form for a moment to sort of point something out here. But this would give us the probability that it's rainy from 2 days, 2 days from now. Now, what's interesting here? Why am I doing this again? And we've already done it. Very suggestively, because I know where this is going. What if I asked you to take this matrix now and find the square of the matrix? AKA, take that matrix and multiply it by itself. What's p squared? Well, it's some matrix, right? It's some 2 by 2 matrix. And you guys should remember how to multiply matrices back from chapter 5. that to multiply a matrix, two matrices, I take the matrix on the left, and I take its rows, and I multiply them by the columns of the matrix on the right. So I'm taking basically the rows of P times the columns of P. And to find, say, I don't know, very suggestively again, let's find this entry in the first row, second column of P squared. What would I have to do to find this entry in particular? Well, that's first row, second column. So I should take the first row of P and multiply by the second column of P to find this entry. So what happens when I do that? What's the first row of P times the second column of P? Well, I'm going to take 3/4 times 1/4 plus 1/4 times 2/3. And that should sound familiar because that's exactly this that we got from the tree diagram. So this, getting the probability from the tree diagram could be reinterpreted as one of our steps in multiplying this matrix P by itself. So finding this probability was just matrix multiplication. So now we start to see why we have this transition matrix in the first place. Not only does it encode each individual probability after one step, but when I multiply by this matrix, it actually encodes probabilities after 2 steps or 3 steps, however many times I want, depending on the power of the matrix I take. So I take the square of the matrix, the numbers I get will represent the transition probabilities for 2 steps as opposed to just 1 step. Okay, so great. If I want to know a probability of transitioning from one state to another after some number of steps, I need to take this transition matrix and take the appropriate power. And then those entries will represent those probabilities. Okay, so that's really good. I'm going to now move away from this example and give us our general definition that I want to talk about of the k-step transition matrix. I'm just going to basically encode this all in a nice definition. So this is the k-step transition matrix. This is the name your book gives to this object. And it's just a matrix, and it is the following. It's taking, it's denoted this way. So when I write P of a K, I mean the k-step transition matrix, and all it is it's just P to the K power, where P is the transition matrix. So I don't know exactly why we use this funky notation instead of just writing P to the K power, but your book and your assignments will use this notation, so I will too, just to be consistent with you guys. So when I say P of K like this, I just mean take the transition matrix to the Kth power. So take K copies of P and multiply them all together. This is the K-step transition matrix, and it encodes the probabilities of transitioning from one state to another after K steps. Or stages, or whatever word we're going to use here, but I'll use steps. So after K steps of the process, all the probabilities of transitioning from one state to another are encoded in this matrix. Okay. So we're going to be able to solve a lot more problems now, because before, the only way that we had to find probabilities was by looking at a transition diagram or looking at a tree diagram and finding all the possible paths that met the criteria of whatever we're looking for, and then multiplying out the probabilities and adding them all up. And for small examples, that worked just fine. But if we want anything bigger or more complicated, it gets really tedious really quickly. Now that I have a matrix that I just need to multiply by itself a bunch of times, this whole process is greatly simplified because, you guys know how to multiply matrices now. It's just a nice definite thing that you just do. I don't have to search for paths or anything. I just multiply the matrix because I know the matrix. Furthermore, you guys have the benefit of this all being online, and so you guys are allowed to use calculators. So if you haven't gotten comfortable with a matrix calculator, you should, because it'll greatly simplify this process of finding powers. It would very much be helpful. I do want you guys to know how to do this by hand. So like on your activities, you'll have to show your work and stuff. And on the upcoming exam, there'll be a couple problems where you have to show work again. And so I may want you to demonstrate to me that you understand how to do this kind of thing by hand. I won't throw anything too horrible at you. I'm not going to ask for like the 10th power of a 5x5 matrix or anything, but you will have to at least show me that you can do this by hand, but feel free, check your work with a calculator and all that. I don't mind. Anyway, okay. So the takeaway is we're going to reduce a lot of these problems down to just finding powers of a matrix. Okay. Cool. So let's see some examples. Okay, some particular examples in mind that I want to look at. Okay, so what I'm gonna do for this example is I'm gonna draw a transition diagram. So we'll have two states that we call A and B. And here are the transitions that we have. This one's labeled 1, this one is 0.2, and this one's 0.8. Okay. So here is our transition diagram for a Markov chain. Some Markov chain has this transition diagram. And here's our question. What is the probability of transitioning from, let's do state B to state A after, we're going to do 3 steps. 3 steps. So we're going to assume that I start at B, and I'm going to ask after 3 steps, what's the probability that I end up at A? So normally what we'd have to do is find every possible path that takes 3 steps starting from B and ends on A. And there might be a bunch of those. I don't know. Maybe not. But we don't have to worry about that anymore because now I can just take my matrix and raise it to a power. So the first step here would be, let's find the transition matrix. So the transition matrix would be this. So these are labeled A, B, A, B. What's the probability of going from A to A? Well, if I'm at A, there's no arrow back to A. So it's 0 because I'm missing that arrow. The probability of going from A to B is 1. The probability of going from B to A is 0.8. And the probability of going from B to B is 0.2. So here's our transition matrix. Again, I'll point out, we could check that each individual row adds up to 1. 0 plus 1 is 1. 0.8 plus 0.2 is 1. So this really does look like a transition matrix. And now I'm asking for a probability after 3 steps. So technically, here's what I need to do is we can find p to the 3rd power, right? That would be sufficient to solve this problem. Is let's find the 3rd power of this matrix. Okay. Okay. So I'm going to do that, and I'm going to point something out at the end to show that we could actually do it a little faster. But let's go ahead and just do it this way first. So first thing I might do then is, instead of finding the 3rd power right away, let's find the 2nd power first. That'll simplify things for us. Let's find the 2nd power. So I'm taking p times itself. So I'll take the first row times first column. That's 0. Hang on. Yeah, okay. 0 plus 0.8. And then first row times second column is 0 plus 0.2. And this adds up to 1, so that's good. Again, the powers of the transition matrix should also have the rows add up to 1. So that's a way to check your work as you go. Make sure your rows add up to 1. These add up to 1, so it looks like we're good. Now I take the second row times first column, that's 0.8 times 0 plus 0.2 times 0.8. I think that's 0.16. And then